Welcome guys. Before we start, be sure to subscribe to my channel. Welcome guys. So today we just solved the Laplace transformation for a lot of functions, and I will write down the write down the time record for each one. Okay, so the first one basically is very simple. We calculate the Laplace transformation of this exponential t. Okay, so this is what we have, right? So this is exponential 1 minus t dt infinity to 0, and this is 1 minus s exponential 1 minus st infinity 0. So put infinity 0, put 0 is 1, right? So this, but it's required that the real s need to be larger than 1. Okay. Second, suppose f of t is 1, when t larger than 0, then we have this. Alright, so Laplace transformation, this is just, so infinity 0 when 0 is 1. Okay. Okay, and only require real s larger than 0. Okay, and this also, people like to write it as the step function, because we only care about this part. Okay, so okay, and then the third one, and basically f of t is just cosine omega t. Okay, so we just write f as this one. Okay, and then do the Laplace transformation for this f. So we get this dt plus half dt. So this give you what? This give you half from the first one, right? From the first one, we know that this is this. So from from the first one. Okay, and also valid for real s larger than 0, right? Because this is imaginary, so we only care about whether this one converge or not. Okay, so number 4, this is, I already solved it, so I just solve it again. Okay, so f of s just equals to this. Okay, and we use the invariant by integration by part. So this can be written as, this is u, this is v prime, right? So this is just u v minus v u prime. Okay, so fs. So this is t to the n minus exponential minus t s infinity 0 plus the known s 0 infinity minus exponential minus st tn minus 1 dt. Okay, so yeah, just straightforward, and this is 0, right? Since the exponential decayed much faster, so you get n over s, and then you see this is Laplace transformation of tn minus 1. Yeah. So which tell you that f of s is just 1 over s Laplace transform of I should write out Laplace transform as this. So we know that f1 we already get is at 1 over s. So this tell you that t to n is just, you just keep using this formula, so you get the n factorial s n plus 1, and there are n, right? So there's n terms, so you will get the n factorial here, and then you will for each once you use this recursion, you get the extra s, right? So you get it. Okay, another comma 1 is comma technique is just written as this. Okay. Okay. Yeah, so this is much of them. Okay, so number 5, this is also a famous example, right? Also easy. So 1 if right, this one, right? So and the else is 0. Okay, so this is also easy just from definition. It tells us that the f of s is just integral 0 to infinity, and this one, right? So f of t. So let's go with the a, b. Yeah, so this is exponential as minus bs over s. Okay, that's it. Okay, and then now we discuss this delta function. Okay, when there's an impulse, so if impulse at t equals 0, then we need to consider this. There's a small 0 minus here. Okay, so this will give you delta t minus exponential t. So this gives you, you just put t equals 0, right? So this gives you 1. Okay, and 8, we compute the f of t to be the derivative of delta t to the kth power. Okay, so f of s is just 0 to 0 minus infinity to 0 minus 0 minus to infinity. Delta k to the t is 1 to the minus sd dt, right? So, and then we do the integration of by part, we get minus k minus 1 to the power k dk dtk is 1 to the minus sd, and put t equal to 0. Okay, so this gives us that s to the k is 1 to the minus sd, t to the 0, which is sk. Okay. Okay, number 9, we are talking about linearity. So linearity is very easy, right? Since L, so let me denote L as to be basically f of s. Basically, it's just this, the Laplace transform. So LAF just ALF, right? By definition, since integration is linear. Also, LF plus G is just LF plus LG. Okay, so this is the technique we need to use. Okay, 10, we compute sine omega t. So 0 to infinity, sine omega t exponential minus st, right? So it's the same technique in 1 over 2i, 0 to infinity, exponential I omega t minus exponential minus I omega t. Is this. Okay. Okay, so this tells us that I to I is 0 to infinity exponential I omega minus st minus exponential minus I omega plus st. Okay, so there are 2 terms. Okay, and the first one give you s minus I omega 1 minus s plus I omega 1. Okay, so this gives you 2i s plus 1 omega squared to is s plus 2i omega. So let me check. Okay, yeah, so this is correct. This should give you this. Okay. Okay, so 11, we talk about the time scaling. Okay, so time scaling is also a fact, interesting result. Suppose I just set g of t to be at, where a is larger than 0. Then what we have is this g of s. Basically, I denoted as the Laplace transform of this. 0 to infinity fat exponential minus sat dt. It's just a 1 over a 0 infinity f of tau exponential minus s divided by a tau d tau. I just do the change of variable, so st equals to tau. So this is just 1 over a, and this is just Laplace transformation but change s over a. Okay, so combination just tell you that the Laplace transformation of fat is just 1 over a. The Laplace transformation of f of t, but s over a. Yeah, so this is just the result. Okay. Okay, so example 12. L exponential. So Laplace transformation of exponential at is just 1 over a and 1 s over a divided by 1. Okay, so it's just s minus a. Okay, so then we talk about exponential scaling. So g of t to be exponential at f of t, then g of s, basically the Laplace transformation of this g is basically f s minus a. So the proof is very simple, since that exponential at f of t plus exponential minus st to do the integration is just 0 to infinity f of t exponential minus s minus at dt. So this is just f minus a. So just write carefully. Okay. Okay, so 14, we can calculate a difficult one that people like to ask. So this exponential minus t cosine t. Remember that the Laplace transformation of cosine t is just s over s squared plus 1 by the previous item. So this is just s minus plus 1 divided by s plus 1 squared. So it's s plus 1, s squared plus 2s plus 2, s squared plus 2s plus 2. Yes, that's it. Okay. And okay, so next we talk about the derivative. Yeah, so the theorem is that if f is continuous at x t equals to 0, right? So Lf prime is just sf of s, right? Laplace transformation of f minus f. F prime. Oh, sorry, f of 0. Okay, f of 0. Okay, so the proof. And you can also calculate the second derivative. Just put the same, just put the results. We can get this one. So how to do? Just put this. Use this one. Right. So we just put f prime prime to be here. Use the first one. So and this is the same as the previous. So s f of s minus f prime 0. So there's no f prime. And minus f prime 0, so this gives you s squared f of s minus f s times f of 0 minus f prime of 0. Okay, and similar, and then we can get okay, similar. So basically, you can get this, but you just keep doing this formula, and then you will get the results. Okay. And I think we don't have, let me check. Okay, so maybe we can still prove it. So f prime of t exponential minus t dt infinite 0 to infinity, just basic f of t exponential s of t. So this is the integration by part. So this is dv, this is u. Okay. So we have uv minus v du, right? So v is f, u du is basically here, plus s. And yeah, okay, so this is 0 to infinity to 0, so put infinity is 0, so 0 putting is f0, right, plus s times Laplace transformation of f. So basically it's just f of s. Okay, so we have proved it. Well, I think let me change. Okay, so example. Okay, so 18 example is basically yeah, I think there's no actual example we need to provide. Nothing is important. Okay, yeah. So one example I want to use is that okay, and in 18, and we need to talk is multiplication by t. Okay, so theorem is that suppose g of t is just t times f of t, then the Laplace transformation of g of s is minus f prime s. Okay, the proof it's very simple since g of t is basically this. Okay, so if you think carefully, if you look it carefully, you will notice that basically d minus d over ds to infinity is exponential minus st equal t dt. Because when you do the differential with respect to s, then there's a minus t will comes down. Okay, so this is the proof. Okay, so let me provide some example. So g of t is exponential of this, right? Suppose f of t is this. So Laplace transformation of this is basically minus ds, right? So by the formula it gives you this. Okay, and also you can compute this by doing the same thing. Just keep doing the second derivative. You get this. Okay, so fact t to k exponential minus t, just k minus 1 factorial s plus 1 and k plus 1. So you're just doing k's derivative. Okay, so now we go into the 19th item. Basically it's the convolution. Convolution is much difficult, so I will not prove here, and I will provide a next video to prove the convolution of the Laplace transform, because which is much difficult. Okay, so that's it. So hopefully you guys like these kind of videos, and be sure to subscribe to my channel. Thanks.